Hello and welcome to the Spacewalkers Live multi-part technical workshop on SPB, Shortest Path Bridging. SPB is an IEEE standard which was originally conceived as the evolution of the aging spanning tree protocol. However, it can do a lot more than that. It can provide Layer 2 and Layer 3 VPN services, similar to those of other technologies such as MPLS or EVPN. However, it is much simpler to configure, deploy, and troubleshoot. We at Alcatel-Lucent Enterprise have further simplified this technology with a lot of automation, and it's fully integrated with Access Guardian, the network admission control framework, making it an ideal choice for zero-trust architectures based on software-defined microsegmentation. Let's review the agenda. In part 1, we will introduce SPB not from the point of view of the protocol itself, but rather some of the reasons why you should pay attention to this technology and where it fits. In part 2, we will go deeper into the technology and present the fundamentals of its data and control planes. In part 3, we will do hands-on and configure an SPB backbone. In part 4, we will look at the services framework. In part 5 is another lab in which we will see how to configure Layer 2 SPB services using the CLI and also from OmniVista. In part 6, we will introduce L3 services, VPN Lite and Layer 3 VPN. And in part 7, we will create a Layer 3 VPN. In part 8, we will discuss different ways in which you can manage an SPB network. In part 9, we will see how to use SPB to create a software-defined campus using OmniVista in SD-LAN mode. Finally, we will close with key takeaways. There's a lot to cover, so let's get started. Welcome to part 1 of this SPB series. In this section, I will present SPB from the point of view of its merits, what it can do for you, rather than how it does it. Hopefully, I will pique your interest such that you will continue watching the rest of the series. I believe it is well worth your time. I'm a big enthusiast of this technology, and I've written the SPB architecture guide, which you will find in the Spacewalkers resource section. There's a lot to cover, so without further ado, let's get on with it.
The first thing to know about SPB is that it is an all-in-one Swiss knife solution. What do I mean by that? It means that you can tackle different problems with it. You can use it in the campus, and in fact, SPB was first conceived as a replacement for spanning tree. Spanning tree is an ancient protocol designed to prevent loops. However, it can be a real source of headaches because spanning tree misconfigurations or errors can result in a complete network meltdown. On top of that, spanning tree is very inefficient and wastes network capacity, resulting in poor performance. SPB came to fix all that with a modern and robust network protocol that makes networks stable and performant. But it's not just the replacement of spanning tree. It adds multi-tenancy with both Layer 2 and Layer 3 VPNs, and that makes it ideal for microsegmentation and for IoT in particular. The second area is the data center. You can use SPB to build data center fabrics spanning one or multiple sites. These fabrics provide any-to-any connectivity over optimal low-latency paths, making it ideal for modern virtualized or private cloud environments. The third area is the WAN. SPB offers Layer 2 and Layer 3 VPN services, which are similar to MPLS services, yet much simpler to deploy and operate. These services can deliver multi-tenanted services to multiple sites connected across the WAN. The fact that you can address all three problems with one solution is quite unique to SPB. Instead of having three different solutions, such as spanning tree in the campus, VXLAN overlays in the data center, and MPLS in the WAN, you can do all three with the one protocol. And this reduces the complexity of managing multiple dissimilar technologies. I mentioned in the previous slide that SPB was initially conceived as a replacement for spanning tree. What was wrong with spanning tree? The first problem with spanning tree is that it creates a single tree. And to do that, it disables multiple links. This is already a waste of capacity. It is also inefficient, resulting in reduced throughput and increased latency because traffic to and from the root bridge will traverse an optimal path, but traffic between other nodes, not including the root bridge, will be forced to take a very long detour across the root bridge, as in the example we see on the slide. The two nodes on the far right part of the slide have a direct link between them, but unfortunately, that link is disabled by spanning tree, which means that traffic between devices connected to those two nodes is forced to take the much longer path passing through the root bridge. An additional problem is not strictly related to spanning tree, but rather MAC learning in Ethernet, which is float and learn and does not have a control plane protocol. For this reason, all nodes in the network learn all client MAC addresses, even if they are not directly connected to any client device. This poses a scalability and also stability problem because as those devices connect, disconnect, move, and reconnect, those MAC tables need to be constantly updated as well. SPB solves all these problems. Firstly, in SPB, there is not a single tree with a single root. There are multiple trees. Every node is the root of its own tree, and for that reason, no links are disabled and traffic between client devices connected to any pair of nodes will traverse the shortest path. That is to say that there are multiple load balancing paths with optimal throughput and latency. In addition to that, core nodes that do not connect to any client device do not need to learn those device MAC addresses. This increases network scalability and stability. What is powering SPB is a link state protocol, ISIS, which is similar to OSPF. But where OSPF is for routed traffic, in SPB, we can benefit from multiple load balancing paths, not only for routed traffic, but also for bridge traffic. SPB is an ideal solution for macro and micro segmentation. First, because it makes it really easy to create virtual segments for different user communities or device types without increasing the operational complexity as you do so. And second, because it's fully integrated with Access Guardian, which is the network admission control framework, such that mapping of users or devices to their segment can be dynamic and policy-driven. If you want to know more about network segmentation, you can visit the link to watch my presentation on this topic. In short, SPB makes it easier to adopt a zero trust framework based on software-defined microsegmentation. The SPB fabric is dynamic, is elastic, and this makes it more secure. Let me illustrate it with an example. In this higher education example, let's imagine that there's a STEM project, which stands for Science, Technology, Engineering, and Mathematics. Since students and faculty will be conducting tests as part of the project, we create an isolated network segment, which we name STEM project. Currently, there's a number of students and faculty working on this project. They have authenticated with their network credentials, and they have access to this dedicated segment wherever they might be, from the lab itself, from the library, or somewhere else around campus. Now, a student wants to work on the project from the dorm. So he or she connects and authenticates to the network. The segment is now automatically stretched so that the student can work on the STEM project from the dorm. At some point, the student finishes working on the project, disconnects, and goes to bed. And so the service automatically contracts. Now let's imagine a hacker wanted to disrupt this STEM project. Well, without the right credentials, the hacker won't be able to connect to the STEM project service and therefore won't be able to disrupt the OS or otherwise hack it. This makes the service inherently more secure. You cannot hack a service if it's not connected. To sum up, services stretch and contract as needed as users or devices connect, disconnect, and roam. The service is only active for the duration of the legitimate user connection. This process is automatic and is driven by the identity and policies attached to those users or devices and does not require any manual intervention. The security benefit is the reduced attack surface because the service is only enabled where and when strictly necessary. There are some additional benefits such as reduced unnecessary broadcast and MAC learning, which result in better performance and higher stability. VPN services provide isolation between those different services, but also those services are isolated from the core. Those VPN services are different virtual logical planes, separate from the physical plane. The core is isolated from the VPN traffic because traffic is tunneled. It is also isolated from service configuration changes, service moves, adds, and changes because services are delivered from the edge and traffic is simply tunneled across the core. So once the core is deployed, no further touches are required. Changes happen only at the edge. So for example, if a hacker attempted to discover or DOS the network, he wouldn't be able to because his traffic is on a different plane and isolated from the core. Moreover, SPB nodes do not use the IP protocol. Of course, they can transport IP traffic, but they do not use it themselves. This provides some additional protection from IP-based attacks and hacking techniques. SPB nodes are simply invisible to IP scanning, DOS, etc. What also enables the use of a single solution for multiple problems is having consistent support of this protocol and related features across all the required product lines. If you compare that with other technologies, let's take MPLS for example, sure, it can be a good fit for the WAN, but you may find that it is not supported on access layer switches or data center switches. And even when it is, you may find those products are lacking other required features such as network admission control. But at ALE, we have SPB support across the board with consistent feature set and operating system. On modular switches with high density and capacity that you can use at core, aggregation, or even the access layer. On compact switches that you can use as a topo rack in the data center or in a spinal leaf architecture, but you can also use as a compact core in the campus. And these switches also provide high capacity wire rate performance in a compact form factor. At the access layer on the advanced access switches that can also be used as a small core, offering multi-gig performance and HPOE while supporting a broad range of access layer security features. And even on environmentally hardened switches for harsh environments with an extended temperature range for challenging EMC, EMI, while still offering HPOE and supporting the same range of features. Finally, it is also supported on the OmniVista NMS to visualize topology, paths, and to configure SPB services through a friendly graphical user interface. Bottom line is that not only SPB is suitable for use in campus data center and WAN, but it is broadly supported across the board with consistent feature set and same operating system. And you cannot say the same about other technologies that SPB is sometimes compared to, such as MPLS or EVPN, because support of those technologies can be patchy. As an IEEE standard, SPB not only interoperates with other vendors' SPB implementation, but it is also backwards compatible and interoperates with other protocols. What this means is that SPB adoption does not require a forklift upgrade. At layer 2, it interoperates with all previous IEEE standards such as L2-L2, Q&Q, or LACP. Therefore, an SPB migration can start at the aggregation and core layers, whilst the access layer can wait until the next refresh cycle. At layer 3, routing in and out towards external non-SPB networks can use standard protocols such as OSPF, ISIS, or BGP. And this is also valid for multicast traffic, which can interoperate through protocol-independent multicast and its different variants. Bottom line, SPB can interoperate at layer 2, layer 3, and not just unicast, but also multicast traffic. And the benefit is investment protection. There is no need for a big bang forklift upgrade because the migration can be performed in phases and aligned with refresh cycles. I definitely could continue talking on and on about SPB scalability, fast convergence, optimal performance, and many other things. But rather than doing that, I want to close this section giving you an idea of the type of vertical and use cases where SPB is deployed today. And this includes universities, government, service providers, metros, utilities, IoT use cases, intelligent transportation, data centers, video surveillance, smart cities, and more.
Let's wrap this section with some key takeaways. SPB comes with service provider capabilities which are similar to those of MPLS. It provides multi-tenancy, it isolates the core from the customer's traffic, and it improves scalability and convergence time compared to other alternatives such as L3 routing and VRF. SPB is also an ideal technology for implementing a zero-trust architecture based on microsegmentation because it integrates seamlessly with network admission control and the software-defined microsegmentation capabilities such that users or devices can be authenticated and mapped to their VPN based on their identities, and that Layer 3 deep packet inspection rules can be dynamically applied to them on the fly. The third point is that these additional capabilities do not come with increased complexity, quite the opposite actually. And this is because it all can be achieved with a single control plane protocol, which results in quicker deployment and simpler troubleshooting. And this same solution is applicable to the LAN, the WAN, and the data center, bringing further simplification compared to using different solutions in each of those blocks. With that, I'll see you in the next section. Welcome to part 2 of this SPB series. In this section, we will take a closer look at the technology in SPB and we'll dissect the data and control planes. Let's define those terms first. In any networking technology, the data plane's mission is to forward user traffic between different ports. The data plane makes no decisions as to what port a frame should be forwarded to. It simply performs lookups on the forwarding database. Forwarding database entries indicate what port or group of ports each frame should be forwarded to and what encapsulation to use. Building or populating entries in the FDB with the right destination port or ports and encapsulation is the function of the control plane. Let's see how that works in SPB.
The SPB data plane uses IEEE 802.1ah Provider Backbone Bridging, PBB, also known as Mach-in-Mach encapsulation. When entering the SPB domain, the PBB header is wrapped around the incoming frame, which can be untagged, single-tagged, or double-tagged. And as I was saying in the introduction, SPB is compatible with previous standards such as 802.1q and Q&Q, also known as provider bridging. The example that we see in this diagram is a frame sent from one device on the far left side of the slide to the device on the far right side of the slide. By the way, I have shortened MAC addresses to 2 bytes for simplicity, but make no mistake, they still have 6 bytes. And this frame will go through different networks that use various encapsulations. Let's do a packet walk. The switch that the device is directly connected to uses 802.1q VLAN tagging and will simply add a VLAN tag. This is what we call the CVLAN tag or customer VLAN tag. As the frame continues its journey towards the right and it reaches the provider bridging network, which uses Q&Q encapsulation, here we add an additional VLAN tag, the SVLAN or service VLAN tag. A new ether type is also added, but the source and destination MAC addresses remain the same. As the frame exits the provider bridging network domain and enters the provider backbone bridging domain, here we add the PBB header. This is the Mach-in-Mach encapsulation that we see in teal color. Let's review the fields in this header and what they are for. The backbone VLAN ID.
a very special type of VLAN that serves as a transport VLAN for the SPB service instances and to connect SPB bridges together through shortest path tree sets. Unlike the standard VLAN domain, which uses float and learn or source learning in the data plane to populate the forwarding database, a backbone VLAN domain's FDB is pre-populated by the control plane, and in fact, there is no broadcast in backbone VLANs or in the SPB domain. The ISID or service identifier. The ISID is a 24-bit number that designates the service instance, tenant, container, or VPN. Different SPB services are assigned different ISIDs and isolated from one another. Each SPB service or ISID is bound to a backbone VLAN. Backbone source and destination MAC addresses. The MAC addresses associated with SPB nodes, that is, the backbone MACs. Within the SPB backbone, traffic is forwarded based on the destination BMAC, the B destination address. End client customer MACs are not learned or used for forwarding within the backbone. So the two new MAC addresses that we see in this header are the backbone MAC addresses of the first ingress SPB node and the MAC address of the egress SPB node. Lastly, there's the ether type for PBB. As the frame continues its journey, the PBB header is removed when it exits the SPB domain, and then the Q-in-Q header is also removed. In the end, the frame is delivered transparently and intact to the destination. Within the SPB domain, that is, between SPB nodes, frame forwarding depends entirely on the outer PBB 802.1AH header, that is, backbone MAC addresses and backbone VLANs, and not on the inner header or customer MAC addresses, CMACs. In fact, the SPB backbone nodes do not learn customer MAC addresses, and this makes SPB networks more scalable and stable. Customer MACs are not learned and therefore do not need to be flushed and relearned when they change or move. SPB uses ISIS or Intermediate System to Intermediate System, a well-known, proven, and widely deployed protocol, particularly in service provider backbones. ISIS is responsible for topology and service discovery. ISIS is an extensible link state protocol which implements Dijkstra's shortest path algorithm for path computation. ISIS extensions for SPB are described in RFC 6329 and include a new network layer protocol identifier as well as a set of type length values, TLVs. In a nutshell, these extensions add support for multiple topologies, allowing load sharing over multiple equal cost paths, and service membership discovery, or in other words, communicating what services are enabled on each SPB node. One important advantage of SPB compared to other technologies is that it requires a single control plane protocol as opposed to a stack of protocols like other technologies do. ISIS is responsible for topology computation, for communicating service membership among network nodes, and can also carry customer routes while still preserving isolation between different customers in the case of Layer 3 VPN services. And this is even when using both IP version 4 and IP version 6. So there is no need to add BGP for VPN services because ISIS can play that role as well. Unlike spanning tree, which creates a single tree rooted at the root bridge, in SPB networks, every node builds a topology tree rooted on itself. This is the key reason why in an SPB network, traffic between any pair of nodes always travels along the shortest path. Let's see what happens when using spanning tree. When using spanning tree, traffic between two nodes does not necessarily travel over the shortest path unless one of the two nodes involved is the root bridge. This is illustrated in the left-hand side, in which B1 is the root bridge. Traffic between nodes B5 and B2, for instance, none of which is the root bridge, cannot use the direct single hop path because that link is disabled by spanning tree. Traffic between these two nodes must take a 3-hop detour traversing the root bridge. In contrast, when using SPB, no link is disabled. Each node is the root of its own tree. Nodes B2 and B5 can simply communicate over the direct single-hop path, while at the same time they can communicate with other nodes over different paths, for example, between B4 and B5. SPB support for multiple trees and multiple active paths unlocks utilization of bandwidth in optimal paths that would otherwise be wasted, increasing throughput and reducing latency. Let's see what happens when we have 3 possible equal cost paths, and we use 3 backbone VLANs to take advantage of those multiple equal cost paths. Let's use the same topology from the previous slide, and now let's see it from the perspective of node B1. Node B1 will build a tree with the shortest path between itself and every other node. As there are in fact 3 different but equal cost paths to reach node B5 in each backbone VLAN, the tree will be different. There is a parameter, the ECTID, which is a number assigned to a backbone VLAN when the backbone VLAN is created. It is used for tie breaking during path computation. Assigning different ECTIDs to different backbone VLANs helps those backbone VLANs build different trees, provided that the underlying topology supports multiple equal cost or shortest paths. Now, let's look at it from the perspective of B5, which also builds a tree with the shortest path between itself and every other node, and it does this for every backbone VLAN. You will notice that for the same backbone VLAN, the path from B1 to B5 is symmetrical to the path from B5 to B1. And this symmetry is a property of SPB, and it happens between any pair of nodes. It is an important property for operations and maintenance. For instance, this means that the one-way delay is just half the round-trip delay, which is not necessarily the case with other technologies that are IP-based, in which the reverse path may be different from the forward path. Now, looking at the two-way path between those nodes B1 and B5, we clearly see how those paths are different for the different backbone VLANs, yet the cost remains the same. In SPB, load balancing is achieved by mapping different services to different backbone VLANs. It is not packet by packet, and a given service mapped to a given backbone VLAN will always use the same path, unless there is a topology change such as a node or link failure that makes the path change. And for this reason, SPB delivers the frames in the same order that they were received. The result of ISIS path computation for each backbone VLAN and node is the forwarding database, which is used by the data plane for frame forwarding. Here we see nodes B5 unicast forwarding database. Bump traffic, that is to say broadcast, unknown unicast, and multicast, will be discussed later in the workshop because I need to explain service concepts before talking about bump replication. As you can see, the path to other nodes depends on the backbone VLAN that we're focusing on, and there's 3 possibilities in this topology with the 3 backbone VLANs.
Let's wrap this section with some key takeaways. SPB uses Mac-in-Mac encapsulation to transparently carry the frames across the backbone. This encapsulation isolates core nodes from client MAC address learning, which results in increased network scalability and stability. On top of that, Service ID in the PBB header extends the number of clients which can be supported to 16 million, well beyond the limits of 802.1q or even Q-in-Q. Unlike spanning tree, which builds a single tree rooted at the root bridge and disables many links in order to do that, SPB uses ISIS, a link state protocol bringing all the benefits of layer 3 routing also to bridge traffic. Thanks to that, SPB can load balance across multiple equal-cost optimal paths with less latency and higher throughput. Lastly, these paths have some very useful properties. They are deterministic, they are symmetrical, they are congruent, and they deliver traffic in the order that it was received. With that, I'll see you in the next section. Welcome to part 3 of this SPB series. In this first hands-on section, we will configure an SPB backbone. You will be amazed at how simple this is. If you are familiar with other technologies such as MPLS or EVPN and the number of CLI commands that are required with those technologies, you will be blown away. So let's do it.
Here is the topology that we will use in the hands-on section. As you can see, we have 9 nodes interconnected in a mesh topology, so we can have multiple shortest paths that we will be able to visualize in OmniVista. To each node, we have connected a virtual machine that emulates a client device and that we will use for testing purposes. This will simulate either a user or an IoT device connected to an access port. Before going to the hands-on part, I want to give you a brief summary of what we need to do in order to set up a backbone. We need to create backbone VLANs, that is, the special kind of VLAN that carries MAC-in-MAC encapsulated SPB traffic. As I said in the previous section, as long as the topology has multiple equal cost paths, we can have different shortest path trees in each backbone VLAN, and the ECT ID is a number or a salt, if you will, that is used in the path selection algorithm to make those paths different. We do not need to configure these ECT IDs. They are automatically assigned by default, but we can change them if we so wish. Next, we need to define one of those backbone VLANs as a control backbone VLAN. That is to say that all ISIS control plane communication will use this specific backbone VLAN. And that's it. It is really as simple as that. On pure core nodes, this is set and forget, meaning there is no need to make any changes when creating services or when making changes to them because services are configured at the edge, not at the core. One thing to highlight is that in this workshop, we do things manually because it is the best way to learn. However, we have AutoFabric functionality through which all this is automated. When nodes are connected, there's a discovery mechanism and an SPB backbone is automatically created between all capable devices. So what happens next? ISIS hello messages will be exchanged over the control backbone VLAN and nodes will become adjacent. They will exchange LSPs and build a topology database. More precisely, every node computes a shortest path tree towards every other node, and this is done on every backbone VLAN such that different backbone VLANs can use different paths when multiple paths exist. And once again, this is one of the key differences with spanning tree because in spanning tree there is only one root and one tree. Another thing to mention that will please those who have never used ISIS is that in fact this protocol does not need to be configured. It will be automatically configured and will run on a separate instance from the one used for IP if it is used. And again, paths are symmetric and congruent, which means unicast and multicast traffic uses the same path. We will talk more about multicast or more precisely bump traffic elsewhere in this workshop. What do we need to do? We will define 4 backbone VLANs. I have chosen from 4000 to 4003. We will choose backbone VLAN 4000 as the control backbone VLAN, and we will enable SPB ISIS on backbone interfaces. Backbone interfaces are the ones connecting SPB nodes. Lastly, we will enable the SPB ISIS protocol. Why use 4 backbone VLANs? You may have noticed in the diagram that I showed before that the topology I'm using supports 4 equal cost paths. So by creating 4 backbone VLANs, we can take advantage of all those paths. If you did not notice that there are 4 paths, do not worry, we will clearly see it from OmniVista. Something to remember is that within an SPB domain, the backbone VLANs and the ECT IDs that you assign to those backbone VLANs, in case you change the default, they must match across all nodes, and the backbone VLAN that you define as a control backbone VLAN must also match, or otherwise those nodes will not be able to communicate through ISIS. What does that look like in CLI commands? I will show you this in a second. But starting with a switch which is blank, that's a total of 4 CLI commands to build the backbone if you want to do it manually, and not a single command if you let AutoFabric do it for you. And yes, that is really all that there is to it. So with that, let's now configure this SPB backbone. All right, I have 9 console sessions with the 9 nodes, and I have pre-configured nodes 1 through 8. So we're going to do the configuration on node 9. And the first command is SPB BVLAN 4000 through 4003 to create the 4 backbone VLANs. Next, SPB ISIS control backbone VLAN 4000 to define backbone VLAN 4000 as the control backbone VLAN for ISIS communication. Next, we need to define which interfaces are going to be used as backbone interfaces on this node, that is, interfaces. So the command is SPB ISIS interface port and then the range of interfaces. And then lastly, we need to enable the SPB ISIS protocol. So SPB ISIS admin enable. With that, we have finished the configuration of our SPB backbone. We can now do some verification on this backbone from the CLI. The first command I want to use is show SPB ISIS interface. And here we can see the 3 interfaces on this node which are running SPB. Some interesting information to highlight is that if you're familiar with ISIS, in ISIS there's level 1 and level 2 or level 1, level 2 nodes. In SPB, we're using level 1 type of adjacencies. Another thing to highlight is that the metric by default is 10 for every link regardless of the link speed. But this is something that can be adjusted and as a best practice should be adjusted to be inversely proportional to the link speed. We have also the timer information for the ISIS protocol. What this is saying is that we're sending hello packets every 9 seconds, and if 3 of those hello packets are missed, then the adjacency will be declared as lost and the topology will be recomputed. Lastly, by default, all SPB ISIS adjacencies are of point-to-point type. However, it is possible to define interfaces as point-to-multipoint, which is useful when overlaying an SPB backbone over a network that does not support SPB. The next command is show SPB ISIS nodes. In short, what this command is giving me is the system name for every node, its system ID, which is the backbone MAC address for every node, the source ID, which is a parameter related to multicast that I have not yet explained, and the bridge priority, which is a parameter that can be optionally configured to influence path computation. The next command is show SPB ISIS adjacency to see the status of each adjacency. This node 9, the one on the right, has 3 interfaces connected to 3 nodes. And for those adjacencies, we can see the status. The name of the node that we are adjacent to, its backbone MAC address, the type of adjacency, which is always L1, the status, whether it's up or down, in this case, all are up, which is good, the interface through which we reach this node, and the hold timer. So The hold timer is the number of seconds after which, if we don't receive a hello from that node, we will declare the adjacency down and recompute the topology table. The next command is show SPB ISIS backbone VLANs. We did configure 4 backbone VLANs, so that is what we see here. Backbone VLANs 4000 through 4003. For each backbone VLAN, we also see the ECT ID, which we did not manually configure, but it was auto-configured by default. The only backbone VLAN that we're using at this point in time is the control backbone VLAN because it is the backbone VLAN that we're using for ISIS communication. The other backbone VLANs are not being used at the moment because we have not yet created any services, which is indicated in this column. There's no services mapped to this backbone VLAN. And there's also no ISIT, which is equivalent to a service mapped to this backbone VLAN. I have not yet covered multicast concepts, so I will not explain multicast related information in the show command output. Lastly, let's have a look at this backbone from OmniVista. In the OmniVista topology application, there's an SPB mode that can be enabled to analyze SPB topologies. For that, we go to map level actions and we enable the SPB network mode. Once we do this, we can analyze topologies. For example, we may want to see the different paths that exist between 2 nodes for the different backbone VLANs. For that, we enable this multi-node selection tool, and then we choose 2 nodes to look at the different possible paths. Here, I will choose nodes 6 and 8 because there are 4 possible paths between these nodes. If I want to look at those paths, I need to select the backbone VLAN that I want to see the path for. For that, I go here, and let's start with backbone VLAN 4000. And that is the particular path for all communication over backbone VLAN 4000 between these 2 nodes. If I change that to 4001, we can see that indeed it is a different path. 4002, once again, another path, and 4003, the last option. Later, when we configure services, we will see that we can do the same thing, not for the backbone VLAN, but for the services that are mapped to that backbone VLAN. So thanks to that, we'll be able to analyze the path taken for a specific service. Next, let's go back to the console to have a look at the unicast table. The command for that is show SPB ISIS unicast table. What's important to understand here is that this table is built in the control plane thanks to the ISIS protocol. So the content of this table right now is the backbone MAC address of all nodes, once for every backbone VLAN. As we have 9 nodes, there's 8 other nodes, nodes 1 through 8, and then we learn the backbone MAC addresses of those 8 nodes once for every backbone VLAN. And that makes 8 times 4, 32, which is the number of MAC addresses that we have learned.
Let's wrap this section with some key takeaways. Creating an SPB backbone is as simple as defining the backbone VLANs, defining the backbone interfaces, and simply administratively enabling the protocol. The rest is all taken care of by the control plane. Nodes use ISIS to discover one another, build adjacencies, form neighborships, and exchange topology information to build one tree per node and per backbone VLAN. Yes, it is as simple as that. And in fact, in the lab, we will see how to do this manually because it is the best way to learn, but the ALE Intelligent Fabric can do this automatically for you without you having to type a single command. Just plug, power up, and see the backbone create right in front of your eyes. With that, I'll see you in the next section. Welcome to part 4 of this SPB series. In this section, we will look at the service concepts. What is a service to begin with? What are the different logical interfaces which are part of an SPB service? How does the same ISIS control plane protocol distribute service membership information across the SPB nodes? Let's continue.
An SPB service represents a VPN or tenant and is uniquely identified by its service identifier, the ISID. Let's define some key concepts. A BEB or backbone edge bridge is an SPB node positioned at the edge of the SPB network that encapsulates customer frames for transport across the backbone network and learns customer MAC addresses. The BEB interconnects the customer network space with the SPB network space. A BCB or backbone core bridge is an SPB node that resides inside the SPB network. The BCB node does not terminate traffic. It is only used as transit. As a result, the BCB does not have to learn any of the customer MAC addresses. An SPB service needs only be created or instantiated on BEB nodes, not on BCB nodes, and only on those BEB nodes servicing locations associated to the service. If you are familiar with MPLS, you may realize that SPB BEB nodes are analogous to MPLS provider edge nodes, and SPB BCB nodes are similar to MPLS provider nodes, or label edge routers and label switch routers. In each BEB node, there are two kinds of virtual interfaces. The Service Access Point, or SAP, is a user-side virtual interface which binds a physical port and specific customer traffic types such as untagged, single-tagged, double-tagged, or wildcard to an SPB service. Multiple SAPs can be associated to the same physical port, thus multiplexing and mapping different customer traffic encapsulations to different SPB services. The Service Distribution Point, or SDP, is a neighbor-side virtual interface which binds an SPB service to a far-end BEB on which the service is instantiated. SDPs are dynamically created in the control plane and only for those far-end BEBs with SAPs for the specific service. By definition, BEB nodes terminate services and have at least one SAP. This is what makes them a BEB. In contrast, BCB nodes do not terminate any services. They only act as a transit node and therefore do not have service access or service delivery points. Other than that, there is no difference in hardware, software, or licenses between BEB and BCB nodes. SPB service membership information is shared across the SPB backbone by way of ISIS TLVs, such that all SPB nodes have a consistent view of the services which are active on each BEB and which backbone VLAN those services are mapped to. Each node then builds a service database. We will later see how this information can be used for BOM traffic replication. Let's imagine we have two customers. The purple customer has 4 locations and is using ISID 66, whereas the green customer has only 2 locations and is using ISID 77. In this diagram, B1, B2, B4, and B5 are BEBs, and B3 in the middle will not terminate any customer traffic, that is to say that it is a BCB, and for this reason it is not shown in the diagram. Let's concentrate on B5, the node on the right. This node has 2 SAPs, one for each customer. They could be on the same or different physical ports. If on the same physical port, then we would have to specify a different VLAN tag combination for each customer. If we look at the green customer with only 2 locations, then B5 also has one SDP which maps to the far-end BEB, B1. So any green traffic destined to the location attached to B1 will be forwarded using this SDP. If we look at the purple service instead, then B5 has 3 SDPs and traffic will be forwarded through the SDP corresponding to the location associated to that traffic's MAC address. We can think of SDPs as a logical tunnel to the far-end BEB because traffic will be MAC-in-MAC encapsulated with the far-end BEB's BMAC, but there is also the IC identifier in the frame, so different ICs have different SDPs, and we only build SDPs for those far-end BEBs which do have the service enabled on them. Within the SPB domain, that is between BEB and BCB nodes, frame forwarding depends entirely on the outer headers. That is to say, backbone destination MAC addresses belonging to SPB nodes and not on the inner header or customer MAC addresses belonging to customer client devices. Within the SPB backbone, backbone MAC addresses are learned in the control plane through ISIS. There is no float on learn. End customer devices, however, do not run ISIS. Near-end customer MAC addresses are learned and bound to a SAP, whereas far-end customer MAC addresses are bound to SDPs. And this only happens on BEB nodes and not on BCB nodes. This binding of customer MAC addresses to SAPs and SDPs does rely on float and learn, similar to what happens on a standard Ethernet switch. The difference is that this is not exactly flooding. Let's see how bound traffic is replicated on a BEB node. BUM stands for Broadcast, Unknown Unicast, and Multicast. There's two ways of treating this type of traffic, and the first and the default is called hidden replication. In this mode, BUM traffic received on a SAP and mapped to a given service is replicated at the ingress BEB and converted to multiple unicast frames. A replica is created for every far-end BEB connected to the same service, and these replicas have the BEB's backbone MAC address as the destination address and are forwarded using the unicast forwarding database. Hidden replicated BUM traffic simply uses the unicast forwarding database and therefore travels along the same path. This property is known as congruency. Hidden replication can be inefficient in terms of bandwidth consumption, but it is efficient in terms of resource usage because it does not require a separate tree or forwarding table. That being said, hidden replication can be optimal in some circumstances, particularly when combined with IGMP snooping, because in that case, replicas are only created when the far-end BEB node has active subscribers for the multicast group. The other mode is tandem replication. In this mode, a separate multicast shortest path tree and forwarding database are created. The multicast shortest path tree is also congruent with the unicast shortest path tree. However, the destination addresses in the multicast forwarding database are multicast addresses constructed as a combination of ICID and the backbone MAC of the source BEB. When a BUM frame is received on a BEB, it is MAC-in-MAC encapsulated with the special backbone MAC as the destination address and forwarded according to the multicast forwarding database. The frame will then be forwarded and it will only be replicated at the fork-out point such that there will not be more than one replica sent on any one link. When using tandem BUM replication mode, even though we're using a separate multicast forwarding database, BUM traffic is still forwarded along the same path as unicast traffic, which means the congruency property is preserved. Tandem replication is very efficient in terms of bandwidth because it will only send a single replica on any given link. However, it is less efficient in terms of resource use because it requires an additional shortest path tree and multicast forwarding database per ICID using this type of BUM replication. To wrap up these two replication modes, as a general guideline, hidden replication, which is the default, is a good choice for most traffic types, except for multicast heavy applications such as IPTV. For those services, tandem replication can be a better choice. The choice of hidden versus tandem replication is made on a per service basis, which means you can keep the hidden BUM replication mode for most services and only enable tandem replication for those services that need it. There is in fact a third replication mode, which is a variant of this mode, which is the tandem *G mode. This mode is rarely used, so I will not explain it here, but if you want to know more about it, please refer to the SPB Architecture Guide and to the EOS Network Configuration Guide.
Let's wrap this section with some key takeaways. Firstly, we have the distinction between BEBs, backbone edge bridges, and BCBs, backbone core bridges. The difference is that on BEBs, you directly connect customers or nodes other than SPB nodes, which are outside of the SPB domain, whereas BCB nodes live exclusively in the SPB domain and do not connect to anything other than other SPB nodes and interfaces. There is no difference in terms of hardware, software, or licensing between BEB and BCB nodes, but services need only be configured on BEB nodes, and BCB nodes do not need to learn any client MAC address. Second, we have subports, which are logical interfaces connecting client devices, and we have SDP ports, which are logical interfaces that you can think of as tunnels mapping to far-end BEBs to which far-end clients are connected to. Subs can be either manually or dynamically created and specify the type of client traffic that will be mapped to a given service. SDPs are always dynamically created by the control plane. Third, there is no additional control plane protocol required to propagate service membership information across the network. Once again, it is the single ISIS control plane protocol which takes care of that. With that, I'll see you in the next section. Welcome to part 5 of this SPB series. In this section, we will configure an L2 service, first using the CLI, and then we will do it from OmniVista. Finally, we will use some show commands to verify the service status. Let's continue.
In this lab, I will configure a Layer 2 VPN service which will be mapped to ISID 1001 and Backbone VLAN 4001. Ultimately, we will configure the service on all 9 nodes, and remember that we have a VM connected to each node on port 1/1/48. So all VMs will be on the same subnet and Layer 2 domain, and they will be able to reach one another directly. This also means that all nodes will be BEBs, as they are all terminating the service. But initially, I will only configure the service on nodes 6 and 8, which means that those nodes will be BEBs, while technically the other nodes will remain BCBs, as they are not terminating a service yet. This will allow me to show you how the transit BCB nodes do not learn any end device customer MAC address. As I showed in part 3, when using Backbone VLAN 4001, the path between nodes 6 and 8 is the one highlighted in yellow, which traverses nodes 3 and 4. So we will verify that those nodes are not learning any end customer MAC address. The configuration on those 2 nodes, BEB6 and BEB8, we will do it by hand because it is a good way to learn. Then I will finish the configuration on the other 7 nodes using OmniVista because that is a lot quicker. At that point, those nodes also will become BEBs. We will of course verify that the service is correctly configured and that VMs can reach one another. A recap on service configuration. Services need only be configured on the nodes that terminate the service and not on transit nodes. In the first part of this lab, we will do that on nodes 6 and 8, and then we will do that through OmniVista in the second part on the remaining 7 nodes. When configuring a service, we give it a service ID. This is a locally significant number in AOS, just like other services such as VXLAN, VLAN stacking, or GRE services also have a service ID. But this is not to be confused with the ISID. The ISID is what identifies the service globally. It is globally significant, which means it needs to match across BEBs terminating the same service. A service is mapped not only to an ISID, but also to a backbone VLAN, which means it will use the shortest path tree of that backbone VLAN. Both the ISID and the backbone VLAN must match on all BEBs terminating the given service. And in short, what do we need to do? We need to define the service access port. This is a UNI physical interface in which you can create service access points that terminate services. This is a tricky one from an acronym point of view because one is service access port and the other one is service access point. One is physical and the other one is virtual, and they are related, but they are different things. Then we need to create the service. We will give it a service ID of 1, and we will map it to Backbone VLAN 4001 and ISID 1001. And we need to define the service access points that map untagged traffic received on port 1148 to the service we just created. We will do this on nodes 6 and 8 to begin with. What does that look like in CLI commands? This is what it is. The first command defines port 1/1/48 as a service access port. The second command creates service 1 as an SPB service using ISID 1001 and Backbone VLAN 4001. And the third command creates a service access point mapping untagged traffic received on port 1/1/48 to the service we just created. And this is only required on BEB nodes that terminate the service, and there is nothing to do on BCB or transit nodes. And yes, it is a super simple thing to do. So let's do this on nodes 6 and 8. So here I have the consoles for node 6, 8, and we're also going to run some commands on node 3. And I also have the consoles for the 2 VMs. Before I start the configuration, I'm going to verify that currently the service is not connected. So obviously there's no connectivity between VMs 6 and 8. So for this test, we're using this interface with this IP address, which is .6 on VM6 and it's .8 on VM8. So I can simply do a ping to VM8, and this is not going to work because the service is not yet active, but we're just going to let it run and we'll see how the ping starts working once I do all the configuration. So we start with BB6, and the first command is service access port 1/1/48. Second command is service 1 SPB ISID 1001 Backbone VLAN 4001, and the third command is service 1 SAP port 1/1/48 column 0 to designate untagged traffic received on this port. We repeat the same commands on node 8. Now that it's done, we can verify that the ping should now be working. And that's correct. So before configuring the service on the remaining 7 nodes, let's use some show commands for verification. The first command I'm going to use is show service SPB. So this command will show me the services that have been locally defined on the node. Clearly, we have only configured one service, which is service 1, and it has it's mapped to ISID 1001 and Backbone VLAN 4001. We did not configure the BAM replication mode, but it's using the default, which is head end. And we have only created one SAP, which is this one here. And the service is up. If I do that on node 8, we're going to get a similar output. On the other hand, if I do it on node 3, there's nothing because we have not locally configured this service on node 3, even though the service does pass through node 3. The next command I want to use is show service port. So let's go back to BB6 and we do show service SPB1 port. And what we see here are the virtual ports, that is to say sub ports and SDP ports. So we have one sub port, which is the one we created, and it is this one here. And this one is defined on interface 1148. We also have one SDP port. So the SDP port is the tunnel mapping the far end BEB. In this case, that's BEB8. And that one is dynamically and automatically configured. So that is the SDP port. And we know that through this SDP port, we're going to reach BEB8 because that's the backbone MAC address of BEB8 using the shortest path tree of Backbone VLAN 4001. And we're going to do that using interface 1153A. The next command I want to use is show MAC learning domain SPB. So with this command, I'm going to see the MAC addresses, the customer MAC addresses learned in the SPB domain. And I can be more specific and I can specify what specific SPB service I want to be looking MAC addresses in. But because we have only defined a single one, we just can use this simple command. And we're learning two MAC addresses. One is VM6 and the other one is VM8. We are now on BB6, which has VM6 connected. So the MAC address of VM6 is learned on a service access point because service access points are local virtual interfaces. So this MAC address here is learned on the service access point that exists on the service access port 1148, while this MAC address here is the MAC address of VM8. And we reach VM8 through BB8, and the SDP is like a tunnel, a virtual interface or a tunnel virtual interface that leads to BB8. If I use the same command on BB3, obviously there's no output here because until now, BB3 is only a transit node, so transit nodes, that is to say BCB nodes, do not learn customer MAC addresses. The last thing I want to do before configuring the service on the other 7 nodes is to show you that even though we have not yet configured the service on node 3, node 3 and all other nodes do know about the existence of the service we created on nodes 6 and 8 thanks to the ISIS control plane. So the command for that is show SPB ISIS service. And here we see that clearly BEB3 does know about the service that we created using IC 1001 and map to Backbone VLAN 4001, and that this service has been defined on nodes BEB8 and BEB6. Okay, so that's it for now on those 2 nodes. Now let's do the rest of the configuration from OmniVista. Back in OmniVista, the first thing to notice is that the topology application in OmniVista, when using the SPB network mode, it also detects the services that we have, in this case, manually configured through the CLI. So these icons here, the first one that looks like an RJ45 connector, showing me the sub ports. This other one that looks like a gear icon is showing me the services. Just like before we were looking at the topology per backbone VLAN, we can also now look at it per service. So for that, I'm going to select the 2 devices that I'm interested in looking at the path between them. I'm going to get rid of that. Now I come here to services and I'm going to select the service. Right now we only have one, so we're looking at the topology for that service. But if we had more, we could see how different services would be taking different paths because we have, as I said before, 4 different possible paths in this topology. We also see here an indication of the number of SAPs and the number of SDPs that exist on the device. Okay, so the next point is we're going to add the service to the other 7 devices. So for that, I'm going to go to Configuration, Services, and through polling, OmniVista has detected the service that we manually configured, and it's this one here. If I click on View Details, it's also showing me what devices this service is configured in. We can, of course, add an entirely new service, and for that, I simply click on the plus sign. But what I'm going to do is I'm going to extend this service to the devices where it's not currently defined. For that, I'm going to click on the Edit icon. If I were defining an entirely new service, I would have to configure the service ID, the ISID, the backbone VLAN, etc. But for this service, that's already done. So I'm just going to scroll down, and under Select Devices, I'm going to click on Add Service to New Devices. I click on the Add button, and I have the option of picking devices from the topology map or using the switch picker. I'm going to go with this option because it is much quicker. So I'm simply going to click on Add All, click on OK. And that's going to take care of the service configuration, but I still need to configure a SAP on those devices. So for that, I'm going to enable this option. We're going to continue mapping untagged traffic received on those ports to this service. So that's indicated by a VLAN tag of 0. I'm going to disable this option because that relates to some parameters that I have not yet explained, and that are a little bit more advanced topics that I have not covered. We have the option of defining the SAP interfaces one by one, which could differ on the different devices, but there's a handy feature which is just using the same port on all devices. And we were using port 1/1/48. So we're going to keep using that. So I'm going to click on the plus sign, and that's automatically adding that port to all the devices. So with that, I can simply click on Apply, and the service and the SAPs will be configured on all the devices. I'm not going to enable the option for UMP access ports because I'm going to leave that for the last part of this workshop, which is the SD-LAN type of deployment. So with that, I simply click on Apply. Let's get rid of this. Let's refresh the status. And now we can see that the service is operational, and we can see the details that the service is in fact operational on all the devices and all the SAP ports. If I go back to the topology map, and I enable the SPB mode again, then we can now see that the service and the SAPs are created on all the devices. So the last part would be to verify that now we have connectivity between all 9 VMs connected to these 9 nodes. Let's go back to the console. So I'm back on VM6. I verified before that we could ping a VM8, but now we can ping, in fact, any of the VMs. For example, 192.168.10.1, which is VM1 attached to BB1, 2, etc. So that's all for layer 2 service configuration.
Let's wrap this section with some key takeaways. First, to create a service, we first need to define the service, we give it a name, we choose an ISID, and we map it to a backbone VLAN, which means that this service will use the shortest path tree for that backbone VLAN, and traffic will be delivered in order. In SPB, we load balance traffic by mapping different services to different backbone VLANs. Second, We define the subports and specify the traffic that we want to map to the specific service. We do it by VLAN tag or combination of VLAN tags. We will see it later in the workshop that we can also do it based on authentication, that is, for example, L2-1X or MAC authentication or even IoT fingerprinting. Third, services need only be created on BEBs and only on those BEBs that connect client to that service. There is no need to do anything on BCB nodes. With that, I'll see you in the next section. Welcome to part 6 of this SPB series. In this section, we will look at Layer 3 service concepts. We will introduce and compare VPN Lite with Layer 3 VPN services. We will look at the different ways in which an SPB node can route depending on its hardware capabilities. Let's have a look.
What is a Layer 3 service? A Layer 3 service refers to a type of VPN service connecting multiple sites in a single any-to-any routing domain, as opposed to a Layer 2 service that connects multiple sites in a single any-to-any bridging domain. In a Layer 3 service, different sites utilize different subnets and require routing to communicate. For multi-tenancy and to keep different customers isolated at Layer 3, each customer service is isolated to its own VRF instance. Unless the use case calls for a Layer 2 service, we should choose Layer 3 services. Layer 3 services can scale more in terms of hosts because the IP address space is hierarchical and can be summarized. However, there are some use cases that require Layer 2, such as, for example, data center interconnections normally require Layer 2 services for HA and for VM mobility. Certain IoT use cases also require Layer 2 services when the IoT device uses broadcast-based or non-IP communication. It is the case of some biomedical devices. But other than that, and unless you have a good reason to go with Layer 2, you should choose Layer 3. The diagram illustrates an example of a Layer 3 service connecting 4 of customer A sites, sites 1 through 4. You will notice that each site uses a different subnet and therefore inter-site routing is required. BEB nodes connecting customer sites are represented with router icons for simplicity. These BEBs have a LAN-facing interface which acts as the local site default gateway, as well as a WAN-facing interface to reach remote sites. All WAN interfaces are bound to a single SPB service and are on the same WAN subnet. Lastly, all the LAN and WAN IP interfaces associated to customer A are bound to the same customer A VRF to provide Layer 3 isolation between different customers. SPB-based Layer 3 VPN services rely on edge routing. Routing is only performed at ingress and egress BEBs. At Layer 3, the WAN represents a single Layer 3 hop regardless of the number of intermediate Layer 2 hops, that is BCBs, in between. SPB simply bridges traffic from ingress BEB to egress BEB along the shortest path. So far, I have only described the data plane, but from a control plane point of view, Layer 3 services come in 2 flavors, VPN Lite and Layer 3 VPN. I'll start with VPN Lite. A VPN Lite Layer 3 service is created by overlaying a Layer 3 routing protocol on top of the Layer 2-1 SPB service. This routing protocol can be OSPF, BGP, or even static routing. The routing protocol runs inside the customer's VRF, and a separate instance and associated configuration is created for each customer. The diagram shows an example of how customer A's Layer 3 service can be created as a VPN Lite service by running OSPF on BEB nodes. In the same manner, if we want to create an additional service for another customer, customer B, we create another VRF for that customer and we add an additional OSPF routing instance on the VRF for customer B. And we do the same for customer C. Since we are using VRFs, these customers can have overlapping IP address space without any issue. So this is what we call VPN Lite. It's simple enough. We create a service linking all BEB nodes where the service is required, and we create a routing instance on all those nodes. For example, OSPF. The nodes will discover one another, they will form adjacencies and route. We do not need to configure a VRF or a routing instance in BCB or core intermediate nodes. Traffic from one BEB node to another BEB node will be bridged across the shortest path created by SPB. That alone, the fact that we do not need to create VRF or routing instances on BCB or core nodes saves a significant amount of effort compared to a legacy architecture using pure VLAN trunking, VRF, and routing, because that would require VRF and routing on all intermediate hops, not just the edge nodes. In a nutshell, the pros of VPN Lite is that it is simple. You can run whatever routing protocol you want, OSPF, ISIS, BGP, or even use static routes. From a routing point of view, it's like interconnecting routers with a VLAN, except it's an SPB service, not a VLAN. However, the cons are that even if we do this only on edge nodes, there's multiple routing instances to configure. In the example I gave, with 3 customers and 4 BEBs, we need to configure OSPF 12 times, and this is only a very small network. If we were using IP version 6 also, then we need OSPF version 3 for IP version 6, and that would be a total of 12 more OSPF version 3 configurations. So that's a grand total of 24 OSPF configurations between IP version 4 and IP version 6. And you can see how this can get complicated in larger networks. So for this reason, there is a better way, which is Layer 3 VPN. SPB Layer 3 VPN leverages the existing SPB ISIS instance to carry customer VPN routes without requiring an additional routing protocol such as OSPF. This is accomplished with additional ISIS TLV extensions. We should note that each customer or tenant is still associated to its own VRF, and ISIS TLVs reference the customer's ISID to preserve Layer 3 isolation between different customers or tenants. This mechanism is described in an IETF draft. For those familiar with MPLS or EVPN, those technologies rely on an IGP, for example, OSPF or ISIS for backbone node reachability, and MP-BGP, that's RFC 4760 for customer VPN route transport. In SPB Layer 3 VPN, ISIS can play both of those roles, backbone node reachability and customer VPN route transport. Using a single protocol instead of 2 results in a network that is simpler to deploy and operate. In addition, when comparing SPB and MPLS, SPB BEB nodes play a role similar to that of an MPLS PE provider edge node, while SPB BCB nodes are similar to MPLS P provider nodes. In particular, SPB BCB nodes do not learn any customer VPN routes and require no VRFs to be created on them. VRFs need only be created on BEB nodes, and customer VPN routes are only learned on the BEB nodes that those customers connect to. When looking at this diagram, clearly the topology and the data plane are the same, and we still reserve a VRF for each customer. The only difference is we are no longer adding an OSPF routing instance for each customer VRF. We are simply reutilizing the already existing SPB ISIS routing instance, which is perfectly capable of keeping customer routes isolated from one another. How do we propagate customer routes across the SPB backbone? Unlike the case of a VPN Lite, an SPB Layer 3 VPN does not require the addition of any routing protocol. Customers' VRF routes are exported to the SPB ISIS instance associated to the customer's ISID and bound to the one IP as a gateway address. Far-end BEBs will import those routes into the local VRF routing table. Therefore, those routes will point to the one IP address as next hop. We should note that this mechanism is applicable and identical for both IP version 4 and IP version 6. This is illustrated here from the perspective of BEB1. We should note that route maps can be used for fine-grained route filtering. At each BEB, near-end customer routes are exported from the VRF and into the SPB ISIS routing instance and are bound to the node's one IP interface. This is the interface that the other far-end routers will have on the routing table as next hop for reaching any subnets local to this node. Similarly, the near-end BEB will import any far-end routes from the SPB ISIS routing table into the local VRF, and those routes will have the far-end's BEB one IP address as their next hop. When routes are exported and imported, they are tagged with the ISID number. So the ISID number isolates routes from different customers in the routing table and is also used to select which routes will be imported into the local VRF. If you're familiar with MPLS or EVPN, the ISID plays a role similar to that of the route distinguisher and route target in MPLS or EVPN. Now, what are the advantages and the disadvantages of Layer 3 VPN? Let's start with the pros. There's no need to configure any routing instance other than the one we already use for SPB. It greatly simplifies configuration and reduces load on the control plane. Convergence time is also improved because there's no protocol overlay and no compounding of convergence times. The convergence time is that of ISIS. What are the disadvantages? Well, there are no disadvantages. So you may ask, why have VPN Lite at all if Layer 3 VPN is better? Well, Layer 3 VPN is great within the SPB domain, but you still need VPN Lite for connecting to external networks that do not run SPB. So the guideline is using Layer 3 VPN within the SPB domain and VPN Lite on border nodes that connect to external non-SPB network. And you can redistribute between Layer 3 VPN routes and VPN Lite routes, and you can also use route maps for filtering if necessary. Before going to the hands-on lab, I want to explain some hardware details. The Alcatel-Lucent OmniSwitch product line has supported SPB since AOS 7.3.1 released in 2012, over 10 years ago. Since then, multiple SPB-enabled platforms have been launched, and each new platform incorporated new advancements in ASICs. First-generation ASICs were not capable of routing and performing MAC-in-MAC encapsulation in a single-pass operation. Consequently, routing between IP interfaces associated to two different SPB services or to a VLAN and an SPB service had to traverse the switch fabric twice. This required an external physical loopback connecting two different switch ports, one port in the VLAN domain and the other port in the SPB domain. IP interfaces could only be associated to a VLAN, not directly to an SPB service. It should be noted that these physical loopbacks can be either physical ports or link ACKs. When using virtual chassis, link ACK member ports can span different units in the virtual chassis for redundancy. We refer to this as two-pass routing with external physical loopback. Second-generation ASICs support a concept similar to that of an external physical loopback, but without requiring a cable connection. One or more physical ports bandwidth is dedicated to the loopback function without requiring a cable to be attached. Multiple ports can be dedicated to this function for additional bandwidth and redundancy. When using multiple ports, ports are configured as a link CAC, and when using virtual chassis, link CAC member ports can span different units in the virtual chassis. We refer to this as two-pass routing with internal front panel loopback. One additional difference between the internal front panel loopback and the external physical loopback is that the internal front panel loopback is a single logical port, not two ports. That is, a VLAN port and a sub port, as in the case of the external physical loopback. But the latest generation ASICs support integrated routing and bridging in the SPB domain in the exact same manner as in the VLAN domain. This means that IP interfaces can be associated to an SPV service directly, and traffic can be routed between two SPV services or between a VLAN and an SPV service in a single pass operation without loopbacks. We refer to this as single pass inline routing. Here we are looking at this from a logical point of view. All products we have launched over the last 3 years or so support single-pass inline routing, which means that the routing and bridging functions are completely integrated and both can be done in a single pass. This is what we see on the left-hand side of the diagram. Here we can create IP interfaces tied to an SPV service, just like we can create IP interfaces tied to a VLAN, and we can route between those interfaces. This is what we will do later in the lab. In all the products that require either an external physical hairpin or a front panel loopback, the bridging and routing functions are separate. There is no integrated routing and bridging in the SPV domain. IP interfaces can only be tied to a VLAN, but not directly to an SPV service. So in order to route between SPV services or between an SPV service and the VLAN, you create a dummy VLAN where the IP interface is created and either a physical hairpin or a virtual loopback to link an SPV service to its associated dummy VLAN. Again, all products launched over the last 3 years or so support the simple case of single-pass inline routing that we see on the left-hand side. And in fact, the first product to incorporate this feature was the OmniSwitch 9900 that has supported single-pass inline routing for much longer than that. And here we see the same thing, but from a physical point of view. The diagram in the middle represents the first generation products which do require a cable to do this function, whereas the one on the left does not, and the one on the right, which is the second generation, requires a loopback, but this is simply done through configuration and without a physical cable, hence why it's shown in dotted line. Well, next, when we do the lab, we will do the case of single-pass inline routing. The other two cases are ancient history at this stage. I'm only explaining it for your awareness in case you have some older devices that you want to use for lab.
Let's wrap this section with some key takeaways. First, Layer 3 VPNs are the most efficient and simple form of Layer 3 service, as they simply reutilize the existing ISIS routing instance without any additional routing protocol, and this is valid for dual stack IP version 4 and IP version 6 running on the same service. Second, VPN Lite is useful to interoperate with other Layer 3 nodes outside of the SPB domain. We can use, for example, OSPF or BGP and cross-distribute routes between L3 VPN routes and VPN Lite routes. Third, SPB-capable OmniSwitches released over the last few years incorporate inline routing and make L3 VPN services as simple as an extra line of configuration. But if you have some other devices on your network, you may need to look at either hairpins or front panel loopback ports on those. With that, I'll see you in the next section. Welcome to part 7 of this SPB series. In this section, we will configure and verify a Layer 3 VPN service. There's a few different ways in which we can build Layer 3 VPN services, and I do not intend to explain all of them, but only the most common one. Let's get to work.
In this lab, we will configure a Layer 3 VPN service using single-pass inline routing capable devices. We reuse the same topology from the previous lab, but the difference is now we are using a different interface card on the VMs. These interfaces have IP addresses which are all on different subnets, and therefore routing is required. This is an overview of the required steps. We need to remove the configuration related to the Layer 2 service we created in the previous lab. We will create a LAN VLAN and tag it on interface 48, which is the interface that the VM is mapped to. We will create the WAN service, which connects all the WAN interfaces in the same Layer 2 service. We will create a VRF dedicated to this service. And we will create LAN and WAN IP interfaces. The LAN IP interface is bound to a VLAN, whereas the WAN IP interface is bound to a service. We will bind the VRF and ISID to the WAN IP interface such that far-end devices point to it when adding near-end subnets to the routing table. And we will configure route, import, and export. Now, as I said before, we will be using a different interface on the VMs. These interfaces are all on different subnets and are mapped to a VLAN tag physical interface. The LAN IP interface on the BEB acts as the default gateway and is mapped to the same VLAN, whereas the WAN IP interface is mapped to the SPB service. This is what we had to do to configure the Layer 3 VPN service. This is an example for BEB 9. The first 3 lines remove the Layer 2 service configuration. The rest is what I just explained. We create a VLAN, which for this device is 1017, and we name it Site 9. We tag it on port 48, which is where the VM is mapped. Then we create a service which uses ISID 1002 and Backbone VLAN 4002. We create the VRF for the service and the IP interfaces. The LAN interface is the VM's default gateway and is mapped to the VLAN that we just created, whereas the WAN interface is mapped to the service we just created. We export routes from this VRF to the SPB ISIS table, and we import routes tagged with ISID 1002 into this VRF. We bind the VRF and the ISID to the WAN interface as gateways such that all remote devices point to it when importing near-end routes. And that's it. Let's do it. I have already removed the previous Layer 2 service, so all I have to do is paste this configuration into the CLI. So I'm back on BEB 9, and all I have to do now is paste the config. Let's do that. And that's it. So now we're going to verify this service. For that, we're going to go to the VRF we just created. It's VRF L3 Service. And the first thing I'm going to do is I'm going to verify the routes. Show IP routes. And as we can see, other than the loopback interface, I have 10 routes because we have one subnet for the WAN interfaces plus one subnet for each of the LAN interfaces. And we have 9 of them. So that's 10. We can now verify that we have reachability to the gateways and to the VMs. For example, .21.254 is the LAN IP interface on BEB1. And that works. And if I ping .1 instead, then that's the VM connected to BEB1. Of course, we can do the same for VM2. VM3, and so on. So that's all good. As you can see, it is really easy. That's all there is to it. And you can have, with only a few command lines, a Layer 3 VPN service without even having to configure any routing protocol because we're simply reusing the SPB ISIS instance.
Let's wrap this section with some key takeaways. First, we need to create an SPB service that will connect all WAN interfaces of all required BEB nodes. Whether we are talking about L2 or L3 SPB services, this is always done on BEB nodes and not on BCB nodes. Second, we need to create one-side and LAN-side IP interfaces on a specific VRF. The one-side IP interface will always map to an SPB service directly on switches that support inline routing, or indirectly, that is to say, sitting on a VLAN, on those that don't. The LAN-side IP interface can also sit on an SPB service on switches that support inline routing, but you can still leave it on a VLAN even when they do. Of course, again, this is only done on BEB and not on BCB nodes. Third, we configure route import and export and the mapping of exported routes to the one IP interface as next hop. In doing that, we simply reutilize once again the existing ISIS routing instance to carry VPN routes across the SPB backbone whilst still keeping them isolated. Once again, the beauty of SPB is that we keep using the same protocol instead of adding another protocol to do this job. With that, I'll see you in the next section. Welcome to part 8 of this SPB series. In this very short section, we will discuss the different ways in which we can manage an SPB network. Let's have a look.
So let's examine a few different ways in which you can manage a network comprised of SPB nodes. I'll start with the simplest cases. And the first one is out-of-band management. If building an out-of-band management network is a possibility, then this is definitely an easy way of managing your nodes. This is applicable to any network, not just SPB. This is ideal and recommended when all devices are within close proximity of one another, such as in a data center. OmniSwitch 9900, 6900, and 6860E and N products have an isolated EMP port that you can dedicate to this function. On other switches, such as the 6865, you can use a standard front panel port, you can pick a VLAN, and you can set an IP address that you use to communicate with the outside world. It is always recommended that you create an additional loopback address as best practice, especially if you have redundant paths. In other environments, creating an out-of-band management network may be challenging, so in-band is preferred. If all SPB nodes support single-pass inline routing, then it is a simple matter of creating an additional management service and VRF. Management IP interfaces will be bound to the management service and VRF. And that's it. The management service is like any other SPB service. However, if your network contains a mix of equipment from different generations, some of which does not support single-pass inline routing, you would need either physical loopbacks or front panel logical loopbacks on those nodes, even if those nodes are BCB nodes which do not need to route, or BEB nodes that only terminate Layer 2 services, because on those nodes, IP interfaces cannot be linked directly to a service, only to a VLAN. So there's an alternative which does not require physical or logical loopbacks. We call this in-band management. How does it work? You still create a separate VRF for management, but you don't create a management service. You can create management IP interfaces and bind them directly to the control backbone VLAN. But these are not your standard IP interfaces though. For one, there is no such thing as flooding on an SPB backbone VLAN. So how does ARP work without flooding? Well, not in the standard way. IP to MAC resolution relies on additional ISIS TLVs. So yes, you can still ping, etc. Just that the underlying mechanism is different. Since there is no broadcast in the backbone VLAN, you can create one large management subnet and put all SPB management IP interfaces in the same subnet. There is also a specific SPB management protocol, and you can import and export and redistribute between this protocol and the protocol that you use in the external legacy management network. Let me illustrate that with an example. In this example, we have our SPB network. All nodes have a management IP interface which is bound to a management VRF and to backbone VLAN 4000, the control backbone VLAN. In addition, we want to manage these nodes from the NOC, which is using a legacy VLAN-based network. So we connect that external management network to the SPB network through two gateway nodes, such that we do not lose management of the entire network if one of them goes down. Since we have redundant paths, we need a dynamic routing protocol, and we need to avoid loops. Let's imagine that the routing protocol that we use on the external management network is OSPF. So on the two gateway nodes, we cross-redistribute between external OSPF management routes and SPB management routes. When we do so, we use some route maps to avoid circular route redistribution. If you're like me, this will be clearer when we look at the configuration. So let's do that. Here's an example for BEB1, one of the two gateway nodes linking the SPB domain and the external management network. Let's dissect this config. In this first part, we create the management VRF. Within this VRF, we create an SPB management IP interface, which is bound directly to the control backbone VLAN 4000. And we create a VLAN management IP interface, which is bound to VLAN 1000 and linked to the port we use to connect to the external management network, port 17 in my example. Lastly, we create a loopback interface. This is best practice because even if port 17 is disconnected and VLAN 1000 goes down, I still have a redundant path to this device and I can still reach it through the SPB network. But for that, I need to use the loopback address because the other address, which is linked to VLAN 1000, will be down. This section is just standard OSPF configuration. It is not the focus of this workshop, so I will not spend time on it. We only need to enable the external VLAN domain interfaces, nothing else. In fact, it is not possible to run a routing protocol such as OSPF on the IP interfaces that are bound to an SPB backbone VLAN. Not that there's any need for that anyway, but just so you know. Next, I have some route maps. One of them matches only the NOC subnet because this is the only subnet I want to redistribute. The other matches all management loopback addresses. Lastly, there's two redistribution commands, one from OSPF to the SPB management protocol and the other one the other way around, and in both cases, I apply the respective route map to avoid circular route redistribution. This is the configuration for the other gateway node, and it is very, very similar to the first one, so I will not go through it, but you will have it in the handout. Lastly, on nodes other than gateway nodes, it's very simple. You only need to create the VRF, the management IP interface in the backbone VLAN, and the loopback. That's all. I hope you now have a clear understanding of how to manage an SPB network. We won't be doing a lab on this, as I think it's pretty straightforward.
Let's wrap this section with some key takeaways. First, if at all possible, especially in a data center, out-of-band management using EMP ports is a great way of managing an SPB or any network for that matter. Second, if that is not possible, and in case all switches support inline routing, the best way is to create a Layer 3 VPN and VRF for management, which is essentially no different from any other Layer 3 VPN service. Third, if some devices on the network do not support inline routing, the best way is using in-band management. This still allows management of the SPB network in-band without any additional hairpins or front panel loopback interfaces. With that, I'll see you in the next section. Welcome to part 9 of this SPB series. In this short section, we will explain the concept of SD-LAN, and I will demonstrate how we can use OmniVista to configure SD-LAN services and dynamically map users and devices to their service based on their identity when using authentication or their IoT fingerprint. Let's have a look.
So what is software-defined LAN? By now, you should understand that with SPB, you can segment or slice your network into multiple Layer 2 or Layer 3 virtual logical segments. For example, as we see on the slide, we can create different services for users or for IoT devices such as video surveillance cameras, door locks, temperature controls, and thermostats. And so in this example, we will create 3 services, one for users, one for security, where we map cameras and door locks, and another one for HVAC, where we place temperature controls and thermostats. How to map users and devices to the right VPN service. This can be done statically, of course, as we have done so far, but that's not practical in modern enterprise environments because users and devices are mobile. They connect, they disconnect, they roam, and they reconnect somewhere else. Users and devices are mobile, so this mapping needs to be dynamic. It can be based on authentication or device fingerprinting. We will talk about this a bit more in the next slide. But with SPB, in fact, we can go one step further, which is microsegmentation. Not all users are the same, and not all users have a legitimate need to access all resources. The same profile which maps users to a segment also includes a set of policies which add fine-grained control over user and device privileges, which are different for different roles such as HR versus finance. This is known as role-based access, and this directly relates to the principle of least privilege. And so, even though cameras and door locks are both on the same segment, they do not need to use the same resources. The camera needs to communicate with the video recorder and the door lock with its server. But there is no need for a camera to communicate with a door lock, just like there is no need for a door lock to communicate with another door lock. These fine-grained permissions are implemented through policies which are part of the profile and dynamically applied to the device after authentication. Mapping of devices and users to their service and to their security and QoS policies can be done in different ways. The first way is what we have done in the labs so far. It's by simply defining SAPs on specific ports and for specific VLAN tags or combinations of inner and outer VLAN tags. But static mapping is not flexible for users and devices that move or environments that are dynamic. The best way is through authentication. Users and devices can be authenticated, ideally through L2-1X using certificates. This is not only dynamic and software-defined, but also secure. Another way is through IoT fingerprinting. Omni switches can very accurately determine the vendor, the type of device, and even the model by examining a combination of factors such as the MAC OUI, the set of DHCP options, and the HDP agent data. These elements constitute a fingerprint, and this, although not as secure as authentication, can also be used to dynamically map a device to its service. Let me illustrate this with a demo. When working in SD-LAN mode, we can do everything from OmniVista without using the CLI. What are the steps? We will create 3 dynamic SPB services. We will create 3 dynamic SPB profiles, Service 1, Service 2, and a restricted service, which is a very limited service for those devices that either fail authentication or for which the right profile has not been defined or applied. We will create matching access role profiles and map those profiles to their dynamic service. We will create an authentication flow that authenticates using L2-1X against the UPAN radio server with fallback to MAC authentication for devices without an L2-1X supplicant. And we will apply the restricted profile as default to devices that either fail authentication or when the right profile is not found. Lastly, we will apply this flow on BEB nodes and on specific ports. And of course, we will test it. Let's begin. So we go back to the same scenario that we worked on during the first service creation lab, except this time services will be dynamic and not static. Services will be dynamically assigned and instantiated after the users authenticate. Users will authenticate either through L2-1X or MAC. Let's do it. The first task is creating 3 SPB profiles, Service 1, Service 2, and the restricted SPB service. For that, we go to Unified Access, Template, SPB profile. I'm going to start with the restricted SPB profile, which I'm going to call restricted. The tag value is 0 because we're going to use this as a UMP profile and we're going to map untagged traffic to this service. The ISID, it's going to be 100,000 and the backbone VLAN 4001. For the rest, I'm going to keep the defaults. I'm going to repeat this task for services 1 and 2, changing the ISID number and the backbone VLAN. So that's done. I have the 3 SPB services. The next step now is creating the 3 access role profiles that will map to these services. For that, I go back to templates, access role profile. And in fact, you see that the restricted access role profile already exists because I use it for other things in my lab. But I'm going to create the other 2. I click on plus. And for the name, I'm going to give it the name of service 1. If I wanted, I could attach a policy list. So in the policy list, I could add ACL or QoS policies. For this demo, I'm not going to do that, but this is how you would do dynamic software-defined microsegmentation, by putting a policy list to allow access to certain resources or to certain applications for this specific profile. I'm not going to do that. I'm going to leave defaults as they are, and I'm just going to hit on create. I'm going to repeat that for service 2. So the 3 SPB profiles are created. The 3 access role profiles are created. The next step is mapping those access role profiles to their SPB profile on the nodes. So I'm going to do that one by one, starting with the restricted profile. I'm going to select it, click on apply to devices. The mapping method is not to map to a VLAN, but to map to an SPB service. And the SPB profile is going to be the restricted profile that we created. I'm going to select the devices that I'm going to be doing this on, and that's going to be VIPs 1 through 9. I'm going to click on OK. And that's done. I'm going to repeat that for the service 1 and 2. Okay, so SPB profiles are created, access role profiles are created, and they are also mapped to their corresponding SPB profile. The next step is creating an authentication flow with 802.1x and fallback to MAC authentication when there is no supplicant. For that, we go to templates again and we go to access auth profile. I'm going to create an access auth profile and I'm going to call it SD-LAN. The AAA server profile that we're going to use is the UPAM server. I'm going to leave 802.1x authentication enabled and MAC authentication enabled. The default access role profile is going to be the restricted profile. The pass alternate is going to be the restricted profile for both 802.1x and MAC. And I'm going to click on create, and that's done. Now I need to apply this authentication flow on the port. And for this demo, I'm going to keep using port 48. I'm going to choose the devices. So for this authentication flow, the port type is not a VLAN port, it's an SPB port because we want to map to an SPB service. So I'm going to change that from VLAN port to SPB port, and I'm going to apply that to all devices. Next, I'm going to enable this flow on the port 48 of each device. click on apply, finish, and that's done. So now all I have to do is test it. Since we're going to do authentication, I have also defined employee accounts for those users that we're going to be authenticating through L2-L3, and also company property accounts for those devices that we're going to be authenticating through Mac. So for example, if I take user Bob is going to be mapped to the service 1. So that's an attribute that's going to be returned by the radio server. More specifically, that is the filter ID. Similarly for Alice is going to be mapped to service 2. So those users will be authenticated through L2-L3. But what happens with devices that don't have L2-L3 configured? So for those devices that will have no supplicant, we can do MAC authentication. So similarly, if I go to company property, I have already defined some of those devices. So for example, let's take the first one. So this MAC address is going to be mapped to this service 2. So that's it. Now, all that I have to do is to test it. To test that, I'm just gonna go to VM9 that is attached to BB9. And VM9 is already configured with L2-L3 and I'm already logged on. So, but at this point in time, the interface card that is connected to port 48 is off. So what I'm gonna do is I'm just going to enable that interface. And that's it, because L2-L3 is already configured. I should already be on the network. And to verify connectivity, I'm just going to launch a ping to VM8. I know VM8, I'm doing MAC address authentication on that one, and I've mapped it on the radio server to service 2, which is the same service that the Alice user that is assigned to this Ubuntu station is mapped to also. So they should be able to communicate. To test that, we can do a ping. And that should also work with VMs 5, 6, and 7. We can test that. That should not work, for example, with VM1 because VM1 is mapped to service 1. So that's it. That proves connectivity works in this software-defined LAN scheme as expected. The next thing we can do is we can monitor this from OmniVista. Let's have a look at that. So the first thing I want to check is that the user Alice has properly authenticated. We can see that from the access record in UPAM. And user Alice is right there. And we can see the name. We can see it was L2-L3 authenticated. We can also see that the access role profile is service 2, as I was saying earlier, that it is connected to BB9, and the last status update was alive, which is good. Next, I'm gonna use the OmniVista locator to locate user Alice on the network. We know she's connected to BB9, but it's also interesting to see it. So we can do a search by username. The username we're looking for obviously is Alice, and I'm gonna do a live search as opposed to a historical search, and then hit locate. And so very quickly we see we found her. I'm gonna change to a different view, which makes the information I'm looking for easier to find. And so here we see that she has the UMP service 2 and the IC is 100,002. So that's it. We've seen how we can dynamically instantiate services and assign them to users based on their identity in an SD-LAN fashion, and how we can do all that directly from OmniVista.
Let's wrap this section with some key takeaways. First, SPB can be used in a software-defined campus or data center network by dynamically instantiating the SPB service and dynamically mapping users and devices to their service. In this fashion, services automatically stretch and contract where they are required, if and when required, as users connect, disconnect, move, and connect again. Second, This is fully integrated with our Access Guardian authentication framework, and what this means is that those users and devices can be authenticated by 802.1x or MAC-based authentication, for example, and the service will be assigned based on that identity. Third, we can do the same with IoT fingerprinting and assign the service not on the basis of identity, but on the basis of the IoT fingerprint. Fourth point, we can of course attach policy lists to the SPB UMP profile to implement microsegmentation policies, a zero-trust architecture based on SPB macro and microsegmentation. With that, I'll see you in the next section. Congratulations on making it all the way to the end of this multi-part series on SPB. I hope by now you are as enthusiastic about this technology as I am. Of course, there is definitely a lot more that could be said about it. So, where to go next? A good place to go next is our SPB architecture guide, which you will find here on Spacewalkers. It will provide you with some additional details and examples, for instance, related to IoT, related to hybrid cloud architectures and shared services, VPNs, etc. On this last topic, by the way, we have a Spacewalkers live session in which I explain how to build a shared services architecture to interconnect your on-prem SPB VPNs with your AWS VPCs. Next, you can check our eDemo portal. Here you can book a hands-on lab to get some hands-on experience with these concepts. There's nothing better than hands-on and trying things on your own to fix the concepts. And lastly, reach out to your Alcatel-Lucent enterprise pre-sales contacts to organize a workshop and see how SPB can help in your network. With that, keep enjoying your Spacewalkers live event. I'm looking forward to interacting with you on this and other topics on the Spacewalkers platform. Take care and see you soon.